Welcome to Cloud Cadet episode number 9. My name is Christoph Limpelaer, and I'm an Amazon Web Services instructor at the Linux Academy. Now, in this episode, I'm joined by Jeff Klukas, who's a data engineer at Simple. Simple is a banking platform, so they have a lot of data to play with. Now, Jeff has a very interesting background in physics, because when he went to grad school, he actually ended up working in experimental particle physics on the Large Hadron Collider, which is a mouthful. The Large Hadron Collider is the largest particle accelerator in the world, and it finally found something called the Higgs boson particle, which is a massive discovery, so I highly recommend that you look it up if you're interested in that sort of thing. But that's not going to be the primary focus of this episode. Instead, we're going to talk about data analytics on Amazon Web Services, especially with Amazon Redshift. Now, how do we go from physics to data analytics? Well, particle physics has been pushing the boundaries of what we consider now distributed computing, and they've been doing that for decades. And working on that experiment made Jeff fall in love with programming and automation and just data analytics in general. So, like I said, Simple has a lot of that to work with, so I wanted to invite Jeff on the show to talk about what he's doing at Simple and what we can learn from that, especially from a Redshift perspective. So, Jeff, thank you so much for being on Cloud Cadet today.
Christoph, thank you so much for having me. It's lovely to be on the show.
So, how about we start off with you just explaining a little bit of what you're currently working on at Simple and what you have been working on at Simple?
Yeah, so I am on, Simple has a data team, which is comprised of both data engineers and data analysts. So from the engineering side, what's the point of having this data team? It's about making all of the information that's going on, the metrics that we have about our business, making those available to humans in some form that it can be used. We can make queries, we can understand what's going on with the business. So that involves my team, the data engineering team. We end up building out pipelines in order to get data from wherever the source is, get it into Amazon Redshift, which is our data warehouse. We're starting to do some more complicated with things with that, but right now it really is focused on Redshift. And Redshift is this central place where we have all of these different data sources. We have copies of backend Postgres databases. We have copies of the data that's coming in through message queues. We have client analytics data that's all getting funneled into Redshift. So it's this one database that allows you to make these queries across these different data sources, and you have kind of a full history of what's going on. So that's used by our analysts to answer questions about what's going on with the product, how do people interact with it, what do we want to build in terms of new features. It's also used by teams like our risk team in order to identify fraudulent activity, see patterns that are going on there, and make changes. Sometimes doing proactive things to prevent fraud in the future. Sometimes it's about figuring out what fraud has happened.
But in order to get data into Redshift, you've got all these different pipelines. And you mentioned a few of them, like the queues and Postgres database and things like that. So, can you mention or talk a little bit more about what those pipelines are and all of the different services that you use in order to do that?
Sure. So Simple's architecture on AWS. So we run, everything is on AWS. Um, we have a great infrastructure engineering team that is primarily responsible for kind of giving us a service platform of like how do we take some bit of code that defines some service, how do we get that up and running, in AWS. So a lot of what we do is services that are running on this kind of service platform that we define that ends up using kind of bits and pieces of the more raw stuff that AWS provides. So we'll spin up EC2 instances. We have a platform for spinning up Postgres on EC2, giving it elastic block storage. So Amazon EBS. And then we use S3 for a lot of things. So we'll do a lot of storing files and sharing some things between services on S3. So we've kind of defined our own platform that uses a lot of the bits and pieces that Amazon provides. There are also some services like Amazon provides Postgres and it's RDS service, and they manage some of that stuff for you. Um, this is partially there's partially a historical component there of when we started building things 6 years ago, what was available versus what's available today. I'm sure that we would probably use more of Amazon's managed services if we were building this whole thing from scratch again today. But there are also times where you want to have that flexibility to really have full control over what's going on using direct EC2 instances rather than managed services. So it's a lot of EC2, it's a lot of S3, and then Redshift is one of the managed services that we really got a lot of value out of
And you can tell they're very
from
aggressively
AWS.
going towards some of those services that you mentioned, like Kinesis, and you have all the IoT suite of services that they're really pushing forward and trying to build more and more because it's such an important aspect of it. So going back to Redshift though, can you explain a little bit more about what it makes you be able to do? So like maybe give some concrete examples of how Simple is benefiting from Redshift and how it's using it.
Yeah, so Redshift, as a category of things, it is a data warehouse. And what is a data warehouse? A data warehouse is generally, it's a big database, and in this case, it's distributed. So what that means is that if you had a Postgres instance, for example, you really can't scale much beyond like a terabyte of data in Postgres. It gets to be a lot of production concerns. It also ends up being slow to query some huge table that's many many hundreds of gigabytes of data. How do you take the concept of a database and make it more amenable to doing analytics type queries where you're potentially you want to get some aggregate out of you know lots of history of information. So that's where a distributed data warehouse like Redshift comes in. So with Redshift, you have a cluster. You define some number of nodes that you have. You can start with a small cluster that's just a few nodes, and it can scale up to hundreds of nodes if you need that. Um, and so it's a SQL. It provides a SQL interface. Redshift was actually it's based on Postgres. It was forked from Postgres at some point. So if you're familiar with Postgres and how you interact with it, you can connect to Redshift with a Postgres client. Um, and so it brings the familiarity of SQL. A lot of people are already familiar with that interface. So you don't have to learn some whole new query language in order to use it. But you also so it's a SQL interface where you can have really a lot of data. You can have it distributed across a bunch of nodes, and when you run a query, it's actually distributing that to each of the nodes. It kind of knows what pieces of the information live in different places. It's able to run all those subqueries in parallel, aggregate them together, and return the result to you. So if you kind of take advantage of that, if you understand how that distribution happens and you write queries that that really understands that pattern, it can return results, kind of blazingly fast over,
So I'm trying to
terabytes of
visualize
data.
what that might look like if we were to put it into a graph or try to visualize it. You've got the data warehouse itself. Is that what the cluster is? Is that like how is a cluster related to a warehouse, and then how is the node related to that cluster? Does that make sense?
Yeah. So so Redshift consists of there will be one leader node, which is what clients actually connect to. So when you're connecting it, as far as there's just this one machine. You're making a client connection to it. You're sending queries to it. It returns results back to you. So it kind of seems like this leader node is kind of the entry point into the warehouse, and then Redshift itself, it's that leader node plus some number of what they call compute nodes. So it's kind of that ensemble altogether. The leader node is taking your query, it's running a plan on it, figuring out how to run it efficiently, and then it's talking to all of these different nodes where your data actually lives. So those compute nodes, they consist of your actual data, kind of pieces of tables, and um, living on disks that are part of that server, and along with compute and RAM in order to do operations on that data. And then so you make some query, it talks to the leader node, it distributes kind of a subquery to each of the compute nodes. They do their aggregation returns some result back to the leader aggregates that all together and sends you back,
And
you know,
that's a
what you
cluster.
actually
That
asked
whole
for in
thing
the
is a
first
cluster
place.
there. All
So
those nodes.
that whole
I see.
thing is a Redshift cluster, the leader node, and then some number of compute
So if I'm
nodes that are all
understanding
kind of
correctly,
grouped together.
as you were saying, Redshift has that leader node, and you've got all this data. So just picture a bunch of data, right? Instead of just querying that data and chipping at it one at a time, you take that data and you break it up into different chunks, smaller, manageable chunks, and then Redshift will scale up the number of nodes it needs depending on how much data is there, and then it will run the SQL query on that. Depending on the leader node is going to be like, hey, the data is there, so run that query here. This data is here, so run that query there. It'll run all those different queries, and then it'll put it back to the leader node and then return that result back to the client. Is that right?
Yeah, that is mostly correct. You know, I'll
Please.
kind of add to that. You know, there are pieces. There's a lot of that Redshift handles for you. Some of the pieces that you have to define is, you know, you have to define, you know, how many compute nodes do you
I
actually
see.
want? You know, how many do you want to pay for? You know, what's your data capacity need? There are a couple of different types of nodes depending on, you know, how much performance you want versus how much storage you need. So that's one thing that you need to keep track of as like an administrator of Redshift. And the other piece is, you know, you get to define how data gets distributed to these different nodes. And so you get a chance to be strategic there in terms of understanding what kind of queries do you need to run, and you know, how can you distribute the data efficiently in order to meet that need, and you know, make successful parallelized queries that can run efficiently across a lot of nodes. So that's where, you know, this idea of like, you know, Redshift presents this SQL interface. It's familiar to you, but you can get into trouble if you just, you know, run queries, you know, expecting results to come back quickly. Um, if you don't understand what's going on, you know, under the hood. So when you create a table in Redshift, you define what they call distribution keys and sort keys, or dist keys and sort keys. And those are really central, very important concepts of Redshift. That's kind of what controls this distributed behavior, and getting good, you know, performance, you know, and good experiences for your end users that are trying to do analytics on it really depends on using the distributed nature correctly. So you get to decide when you create a table, you pick some column to be the distribution key. So maybe in our case, at least it's simple, we use a user ID in a lot of cases. So so if you have, you know, several tables, they're all distributed on this user ID column. That means that, you know, for any given user ID, data is going to be, you know, co-located on the same compute node. So if you have three tables, you've defined the user ID to be the distribution key. That means for, you know, user ID 12345, its data is always going to end up on the same compute node. So if you end up needing to join between those three tables that use, you know, user ID as their distribution key, all of that data for user 12345 exists on the same node. It's very efficient to do that join between the tables. However, if you want to join some table that is not distributed on user ID, then that means that Redshift now has to do a bunch of communication between nodes,
What
and
about
your
if
query is
you
potentially
if
very
you have that same
expensive.
scenario, but excuse me, you're running the queries on one of the nodes only because you chose that partition key to have all the data in the same nodes. So instead of distributing that data across all the nodes, you're really hammering that same exact node over and over again, and so you're not using the resources. Is that right? Is that an actual problem? Is that how it distributes it?
Um, it, it is certainly possible to end up with kind of skew where your queries are hitting, you know, one node very hard, and not hitting other nodes. This is actually a situation that we've run into. Um, in particular when we've chosen some distribution key like user ID, but the raw data includes null values. So if you have, you know, some high proportion of the user IDs that are coming in are actually nulls, all of those nulls end up going to the same compute node. So you can end up with, there are some cases where we've ended up like, it seems strange, this one compute node, you know, it's at like 70% of its disk capacity, where all, you know, all the other compute nodes are at like 30% disk usage. And it ends up being because you have some table where half of the records that are coming in are all going to the same node because you didn't understand that, you know, there's this one particular value that tends to get a lot of hits. So that hurts you in terms of where data is stored, and it also hurts you in terms of how much work that node has to do
That's
when
actually
you're trying to
very
return
similar
results.
to the way DynamoDB does it. So you have the partition key and the sort key, or just a partition key. And DynamoDB uses an internal hash function using that partition key to distribute that across the hardware. So if you have X amount of capacity for a table, it will distribute that capacity across those nodes. Or I'm not sure if they call them nodes, but this is the same concept. So that sounds very similar actually to the way they're doing it to
Yeah.
Redshift. So that's good. If you're coming from that background, that's probably pretty helpful in understanding a little bit of how the performance works there, right?
Yeah, that does sound very similar, and I think that pattern generally of using a hash function on some value in order to determine where is this piece of data going to live is a pretty common pattern for
Now,
distributed
so you
systems.
mentioned the pipeline earlier with all those different services that just feed the data into Redshift. And before this episode, you told me that one of the things you're working on is making that pipeline completely automated and very robust. So what's not automated and robust right now, and how are you working to fix that?
Yeah, so it's turning out that one of the most important sources of information we have is our backend Postgres databases. So we have Simple has a service-oriented architecture for the actual banking platform type of stuff that we do, and it becomes very important knowing what data exists in there. So each of those services generally has a Postgres database, and we really want to get a pristine copy of what's going on in each of those services databases, get those copied into Redshift so that we can make these queries across things. So we're leveraging a new feature of Postgres, I guess within the last year, called logical decoding, where you can actually get this whole stream of changes that are happening in Postgres, and you can pipe those somewhere else. So we've got that implemented. We're rolling that out across our services. So we now have this pipeline where we can get exactly the list of changes that happen in Postgres, get those into Redshift. But there are some details in that pipeline that you need to hammer out. One of them is that you need to define the tables in Redshift that are going to hold this information from the tables in Postgres. So you need to before you can load data into Redshift, you need to have that source. You need to have a table in Redshift that mirrors the structure of what's going on in Postgres. So you can kind of dump the schema from Postgres, do some translation into relevant types for Redshift, and create that in Redshift. But that's just a point in time, and that's a problem for us right now. Is that we've done that kind of schema dump, and you know made that kind of a mirror schema in Redshift. But then what happens when there's a migration on that source database that adds a table or adds some new columns to an existing table? And it's become very difficult. There are dozens of services that we have, and it's just not tenable for us to keep up with what changes are going on in different databases, and then having to hand write migrations in order to get our Redshift source tables, you our Redshift tables up to date with what's going on in the source. So that's a big thing that we want to automate that process, be able to detect, hey, a column was added in this Postgres database. We need to add that same column in Redshift. And right now there's human intervention needed there, and that's something we want to fix. The other big thing that's an exciting possibility is uh, there's some reconciliation kind of jobs that we want to do where we want to check like, hey, these different services, you know, these financial transactions happened, and did we see them everywhere? Does that all make sense? Like, is it consistent between all of our different services that this transaction did happen, and that the balance that came out of it, for example, is what it should be across all of our services. Um, so we really want to be able to use Redshift for that, but if you want to make a report on that and really feel confident in the results, you need to have high confidence that like all of the data that happened in Postgres really is here in Redshift. So we're working on ways of verifying, what actually happened in Postgres versus what's in Redshift, and that's partially about like every each of these items that happens in Postgres there's a number associated with it called the log sequence number. And we're working on a system to make sure that we're extracting that number, getting that into Redshift, and then finding a way to verify, like we know that there's this whole list of, log sequence numbers that we should have seen from the source Postgres database. Do we see all those same numbers in Redshift? And coming up with an automated way to say, before we run the reconciliation job, yes, we know that we have absolutely everything up until a certain point of time, and we have high confidence that we can run this job, and any discrepancies that exist in the source databases, we're
Now
going to
you're
see them here
using
in Redshift
Postgres,
too.
but if for some reason a company or someone wanted to use something else, are there other alternatives that we can use with Redshift apart from Postgres or maybe MySQL? Are there other services we can use?
Yes. So there are. This is actually an interesting new product that Amazon has. They have a database migration service, which the DMS, the database migration service itself, isn't new. It's existed for a while, but Amazon has been building out the functionality there. And one of the recent improvements that's exciting is that they've added Redshift as a destination. So the general idea of DMS is that you point it at some source database and you point it at some target database, and it moves data from one place to the other, or it copies data from a source to a destination, and it can do that across different types of databases. So I think the use case has largely been, hey, you have this existing database in your own infrastructure, you want to move into an Amazon RDS instance of MySQL or Postgres, something like that. It gives you a way to copy that data. But with the Redshift functionality now, uh, that provides a pipeline where you can have Postgres databases or MySQL databases, and there are a couple other data stores that they support. You can have those in Amazon's infrastructure and use DMS to get this continual copy process going into Redshift. So they provide Amazon provides an automated solution for that now. And again, this is one of those things, like if we were building our architecture today, we probably would be using DMS to do this sort of thing. But because we have an infrastructure for running Kafka and and Postgres on our own, it makes more sense for us to kind of make some changes to our own pipeline in order to provide
I see.
similar
So in this case,
functionality
you
to what
can't
DMS
actually just
provides.
plug DMS into the current pipeline you have because it would make too many changes. So instead, you have to kind of try and mimic what DMS is actually doing.
It's similar. We probably could plug DMS into what we're already doing, but because we're already doing
Sure.
kind of 80% of what DMS would be doing. um, yeah, it kind of makes sense because we already understand that system, and it is nice to have that extra level of control over it. Kind of DMS
Mhm.
would be this additional thing that we're doing, so it makes sense for us with the environment that we have to invest a little bit more into making our existing pipelines do what we need them to do, rather than adding DMS as an additional, you know,
Sure. At least this way, you have a lot more customizability. At least I would think you would because you're literally building it yourself, so you know exactly what goes in and what goes out. Whereas a lot of times when you're using a service like that offered by Amazon Web Services or really any other platform, it's a little bit more of a black box. So they'll give you some flexibility, but there's only so far that you can go with it. You can't really have that customizability. So I could see that being pretty beneficial. But in the case of maybe a smaller company or a one person team or two-person team, if you don't have those resources, having a service like that can really help you out. So knowing how to use it can propulse you forward really quickly. And then in the future, if you need to come back and fix it up, then or change it, then you could dedicate more resources to it. So yeah, I see what you're saying there, definitely.
yep, yeah, and that is kind of one of the central concepts of that just makes engineering a difficult thing, is you have to be making those decisions all the time of what do you want to build yourself, what do you want to use that's managed, and understanding the benefits and liabilities of those two things. And it can be, I'd say that's one of the most stressful things about making infrastructure decisions, is that you just can't have complete knowledge about how this is going to work
Unfortunately.
out for you. And sometimes, yeah, and sometimes you need to try something, and it doesn't work out the way you needed. You try a managed service, and you just end up needing something that's more customized, and you end up having to build it yourself. But it is certainly nice to have managed services available. as an
Awesome. So
option for a
you
lot of
just to
things
wrap
these
up, you
days.
mentioned monitoring services, including Redshift, and I know Redshift has events that can trigger notifications. So is that something that you're using right now, or is it something you can use to monitor, or is it just plugging into CloudWatch or using a third-party service like that? How does that work?
So we utilize some of the CloudWatch metrics that Redshift publishes. Those metrics are mostly about kind of compute node level things of like what's the disk usage, what's the network throughput, those sorts of things, which can be nice, symptoms to help you understand, where are problems happening and all that. So we use Grafana as a front end to visualize some of those CloudWatch metrics. There's also a bunch of metrics that Redshift presents through its SQL interface. So it has system tables that you can query, and we have a service set up that does periodic queries to those system tables and emits them as metrics that we can also visualize in Grafana. And we do some alerting based on those metrics that we get into our pipeline from that. So that's kind of what our outlook for
Awesome. Well,
metrics
Jeff,
on
thank you so
Redshift
much
looks
for your
like.
time. I really appreciate you coming on here and teaching us about Redshift. I've learned a lot, like I said earlier, and I just really appreciate your time. If people want to reach out to you or if they have any other questions related to either Simple or Redshift or anything like that, how would you recommend they reach out to you?
You can find me on Twitter at Jeff Klukas, JeffKlukas.
Jeff, thanks so much for being on Cloud Cadet. I really appreciate it. And thank you, everyone, for tuning in. I hope you have a wonderful day.
Thanks, Christoph.